The moon doesn't spin, or at least not in the way most people imagine. For more than 4 billion years, it has held one face toward Earth unmoving and familiar, as if frozen in time. This steady gaze is no accident. It's the result of gravity friction and orbital mechanics settling into a perfect and ancient rhythm known as tidal locking. Tonight, we're going to drift slowly through the real physics behind that stillness. Step by step, we'll explore how the moon locked its early rotation, how Earth's gravity shaped its motion, and why one hemisphere will always remain hidden from us. Quiet, precise, and grounded in real data, a gentle journey for your mind. If this calm exploration brings you peace or teaches you something new, you're soft like your quiet tap on subscribe, or even a small comment means more than you know. Thank you for being here. Now let's begin. Part 1. If the moon doesn't spin, why do we only ever see one side? Most of us grow up believing the moon is motionless. Night after night, we see the same craters, the same patterns of light and shadow. The face never changes. But this stillness is an illusion. The moon does rotate, but at exactly the same speed that it orbits Earth. This perfect match is what scientists call synchronous rotation, and it's the key to tidal locking. Based on measurements from NASA's Lunar Reconnaissance Orbiter, the moon turns on its axis once every 27.3 days, precisely the same amount of time it takes to complete one trip around Earth. Because those two motions line up so perfectly, the same hemisphere always faces us, while the far side remains turned away. But it wasn't always like this. In the moon's earliest days, likely after it formed from the debris of a colossal collision between Earth and a Mars sized body called Theia, it spun much faster. A lunar day may have lasted only a few hours. But Earth's strong gravity stretched the young moon, slightly pulling it into a shape that wasn't perfectly round. That small distortion created internal friction, like a brake slowly tightening over millions of years. As the moon tried to rotate, Earth's gravity tugged on that bulge again and again, draining rotational energy until the moon's spin slowed to match its orbit. And once the two periods became identical, the braking effect faded. The moon slipped into a perfect gravitational rhythm, one rotation for every orbit, and it has stayed locked that way ever since. That is why you and I and every person who has ever lived see only one lunar face, not because the moon is still, but because it spins with exquisite precision. NASA refers to this perfectly matched behavior as synchronous rotation, a state where the moon's spin rate and its orbital motion fall into complete harmony. In this balance, the moon's angular velocity, the pace at which it turns, is exactly equal to the speed at which it circles Earth. The effect is almost hypnotic. As the moon moves around us, it rotates just enough to keep the same hemisphere pointed toward Earth, like a dancer who never breaks eye contact with her partner. We can see this clearly through numbers. The moon travels through space at roughly 1 kilometer per second, and its 1 month rotation period corresponds to a spin of only 0.037 degrees per hour. That's an incredibly slow turn, so slow that a full lunar day lasts nearly 4 Earth weeks. It is this precise matching of two motions that creates the illusion of stillness in our sky. And the moon is not alone. Across the solar system, tidal locking is common. Jupiter's moon, Io, Saturn's moon, Titan, and Pluto's companion, Charon, all keep one face toward their parent bodies. But Earth's moon stands out because of how large it is compared to the planet. It orbits a proportion rarely seen. Despite that, it settled into an exquisitely stable rotation orbit rhythm. If you've ever watched the moon closely through a telescope and noticed its limb shifting slightly from night to night, you've witnessed libration. This gentle wobble comes from the moon's tilted axis and eccentric orbit. Because of libration, we can glimpse about 59% of the lunar surface over time, even though only half should be visible. It's a quiet reminder that even in apparent stillness, small motions continue. Tidal locking isn't just theory, it's been confirmed through direct measurement. NASA's Grail mission, which mapped the moon's gravitational field in exquisite detail, found variations in density and crust thickness that match predictions of long-term tidal heating and deformation. These patterns, fractures, stress lines, subtle distortions, are the moon's geological diary, recording billions of years of gravitational stretching. Dr. James Williams of NASA's Jet Propulsion Laboratory once summarized it beautifully. Tidal locking is nature finding stability by giving up energy. As the moon shed rotational momentum, it drifted into a quieter, more balanced state that it will likely maintain for eons. To picture this, imagine standing on the moon's near side, the hemisphere facing us. Earth would hang in the sky like a suspended lantern. It would never rise or set. The stars would wheel overhead, but Earth would remain fixed, unmoving, glowing. That is tidal locking made real, an eternal view of home. On the far side, the story is reversed. Earth never appears. The sky there has never held the blue-white world that shaped the moon's destiny. It's a landscape lit by starlight alone, untouched by the presence of its parent planet. This symmetry feels almost poetic, even though its cause is purely physical. Every crater, plain, and shadowed basin on the moon's near side has spent billions of years facing Earth, quietly absorbing micrometeorite impacts and reflecting sunlight back across the void. A world held in place not by magic, but by the steady, patient pull of gravity. Meanwhile, the far side, rougher, older, more heavily cratered, remains forever hidden from our view, living in a kind of permanent obscurity. This contrast between the familiar near side and the untouched far side is one of the most striking consequences of tidal locking, and it's not just a visual curiosity. This fixed orientation has quietly influenced Earth itself in ways far more important than most people realize. The moon's gravitational pull raises tides, stabilizes the tilt of our planet's axis, and gradually slows the Earth's rotation. Without this steadying presence, our days might be shorter, our seasons less predictable, and our climate far more chaotic. What looks like a simple stillness in the sky is actually one of the key reasons Earth has remained a stable, habitable world for billions of years. Astrophysicist Neil deGrasse. Tyson once remarked that the moon is not merely a companion, but a regulator that helps make Earth livable. To the unaided eye, its motion appears peaceful. To scientists, that calmness is the result of rotation slowed to an exact, exquisitely tuned equilibrium. And that is what makes this phenomenon so compelling. The moon's apparent immobility is not a lack of motion at all. It is the most refined form of motion nature can produce. The next time you see that faint silver circle hanging in the sky, remember that it isn't fixed or frozen. It turns and orbits at the same time, moving with a precision shaped by gravity over eons. With that foundation in place, we can now step deeper into the mechanism behind this perfect balance, the invisible force that keeps the moon locked to Earth. Part 2. What invisible force keeps the moon locked forever? There is no enchantment behind the moon's stillness, only gravity, steady and ancient. It makes no sound, shows no flash yet. For billions of years, it has shaped the motions of entire worlds. The moon is one of its most quietly transformed creations. To understand why the moon stays locked, we return to the laws that describe nearly all motion, Newton's law of universal gravitation and Kepler's laws of orbital mechanics. Newton showed that every object pulls on every other with a force proportional to their masses and inversely proportional to the square of the distance between them. The familiar formula F equals G, M1, M2, R2 looks simple, but behind it lies a slow, relentless exchange of energy that spans the moon's entire history. When the moon first condensed after the giant impact with the protoplanet Theia, it spun much faster than it does today, perhaps completing a full rotation in just a few hours. Its outer layers were moving at extraordinary speeds relative to its core. But Earth's gravity did more than pull, it stretched the moon very slightly, creating two tidal bulges, one facing Earth and one on the opposite side. Because the moon was rotating quickly, those bulges could not stay perfectly aligned with Earth's gravitational pull. They drifted slightly ahead or behind the direction of the force, depending on the rotation. This misalignment generated tidal friction, a subtle internal resistance that converted the moon's rotational energy into heat. NASA's Lunar and Planetary Institute describes this process as a vast natural braking system. Over millions of years, the torque produced by Earth's gravity steadily reduced the moon's spin. As the rotation slowed, the tidal bulges gradually shifted into alignment with Earth's pull. When the rotation period finally matched the orbital period, 27.3 days, the braking ceased. The system reached equilibrium and the moon became synchronously locked. Early in its evolution, the gravitational torque acting on the moon may have been around 1016 Newton meters, enough to warm its crust and upper mantle. The heat has long since dissipated, but the evidence remains etched into the lunar surface. Fractures, variations in crust thickness and density, asymmetries that still point back to the ancient tug of war with Earth. Scientists today simulate this long evolution using advanced tidal dissipation models, numerical tools that measure how internal friction converts motion into heat over geological time. These models suggest that in the moon's early life, the amount of rotational energy it lost was staggering. Tens of gigawatts of heat may have been produced inside its crust and mantle, the equivalent of thousands of continuous volcanoes burning beneath its surface. Because of this steady drain, the moon's spin slowed almost imperceptibly, centimeter by centimeter of rotational deceleration each year until it finally matched the 27.3-day orbit we observe now. Dr. James O'Donoghue of JAXA puts it plainly, tidal friction is one of nature's slowest engines, but it never stops. Its purpose here was simple yet profound, to transform a quickly spinning young world into one that turns in perfect synchrony with its path around Earth. From a physics perspective, the process is governed by the conservation of angular momentum. The Earth Moon system has a fixed total amount of rotational and orbital momentum. As the moon's interior dissipated energy through friction, some of that angular momentum shifted from its spin into its orbit. The rotation slowed, the orbit expanded. That transfer continues today. Laser ranging reflectors placed by Apollo astronauts reveal that the moon drifts away at roughly 3.8 centimeters per year, slow enough to feel eternal, yet significant enough that over hundreds of millions of years, tides and day length on Earth will noticeably change. ESA researchers sometimes describe this as a quiet, endless dialogue between Earth and Moon. Gravity pulls, resistance pushes back, energy is lost, momentum shifts. What remains is not stillness, but a stable pattern motion maintaining motion. This same tidal mechanism appears across the solar system. Jupiter's moon Io experiences such intense gravitational stretching that its surface is constantly torn and reheated, producing the most active volcanism known anywhere. Our moon once endured a gentler version of this. The broad dark mare basalts, those smooth plains we see from Earth, are ancient lava fields formed between 3 and 3.5 billion years ago. They are geological proof that internal heat once surged beneath the lunar crust, generated in part by tidal flexing. In this way, the moon's lock is not coincidence. It is the natural outcome of gravity and time. Give a planet and its satellite long enough, and the system will inevitably settle into synchronous rotation, the most stable arrangement allowed by Newton's laws and described beautifully by Kepler's second law of orbital motion. There is also an astonishing precision to this lock. The moon's center of mass doesn't lie exactly at its geometric center. It sits about 2 kilometers closer to Earth. This offset helps the gravitational coupling snap into place and remain secure. Over billions of years, the moon's interior mass distribution seems to have shifted and hardened under repeated gravitational stretching, reinforcing the alignment. Even the tiny oscillations we call libration don't break the lock. The synchronization holds with millimeter level accuracy. Modern missions have confirmed the geological signatures of this history. NASA's Grail mission mapped the moon's gravitational field with extraordinary resolution and revealed subtle variations that align with models of tidal heating and internal flexing. Beneath the surface, the patterns of ancient magma flow match perfectly with what gravitational stress would have produced. In other words, the evidence is everywhere, from orbital mechanics to crustal chemistry. The moon's still face is not an accident. It is the final shape carved by 4.5 billion years of gravitational sculpting. Dr. Maria Zuber, principal investigator of the Grail mission, once explained that the moon's gravity field is a record of a world shaped more by Earth than by itself. And that simple line captures the core truth behind everything we've explored so far. The moon isn't an isolated object drifting quietly through space. It is the product of billions of years of Earth's influence pulled, stretched, slowed, and sculpted by our planet's gravity until it became the world we see today. Seen from far away, perhaps from a passing spacecraft, the Earth Moon system looks like a pair of bodies caught mid dance, Earth spinning quickly, the moon circling slowly, both locked into a shared rhythm. Yet beneath that calm choreography, the forces that shaped the moon long ago are still quietly at work. Earth's own rotation continues to slip just as the moon's once did. Tidal friction in Earth's oceans drains roughly 3.7 terawatts of energy every year, heat produced simply because our oceans rise and fall under the moon's pull. Over immense spans of time, this drag slows Earth's spin and pushes the moon ever farther away. If nothing interrupts this long process, then billions of years from now, Earth will slow enough to become tidally locked to the moon as well. One hemisphere will always see the moon hanging in the same spot in the sky. The opposite hemisphere will never see the moon again. That is the quiet authority of gravity. It doesn't force or shout. It simply persists, patiently reorganizing worlds one fraction of a rotation at a time. As Carl Sagan often reminded us, gravity is the architect of the cosmos. It builds, it balances, it binds, and it does all of this invisibly. The moon's apparent stillness is not a sign of inactivity, but the outcome of 4.5 billion years of gravitational tension and release a negotiation between two worlds carried out in complete silence. And even now, the lock is not absolutely perfect. Solar tides. The moon's elliptical orbit, the gradual drift of Earth's rotation, these subtle influences continue to shift the balance by tiny, almost undetectable amounts. We do not see these changes, but the moon's orbit and orientation are always adjusting, always refining themselves. What seems permanent to the human eye is in truth a slow, continuous motion layered across unimaginable spans of time. So the next time moonlight falls across your window, remember this. Every glint, every shadow, every passing phase is the visible trace of ancient mechanics that began when the solar system was young. The calm we see is the final shape of a process that once shook worlds. And if one invisible force could take a molten, rapidly spinning young moon and freeze its face toward Earth forever, then it's worth asking what that same force has done to the moons of other worlds, where gravity's pull is stronger, the tides are harsher, and the locks are even older. Part 3. Did the moon ever spin freely in the past? The moon we know today seems timeless, always showing the same face, always steady, always familiar. But in its youth, it was anything but calm. Long before it entered its present lockstep orbit, the moon spun like a freshly cast ember, drifting away from the furnace of early Earth. Its crust was molten, its rotation fast, and its surface reshaped constantly by the gravitational tug of the planet that had just created it. To trace that transformation, we return to the moon's violent birth. According to the giant impact hypothesis, roughly 4.5 billion years ago, a Mars sized protoplanet named Theia struck the young Earth with enough force to melt vast regions of the planet's surface. The collision hurled vaporized rock and debris into orbit. Over time, that material gathered under its own gravity and formed the moon. NASA supported simulations, including extensive supercomputer modeling at Ames Research Center, indicate that the newborn moon rotated rapidly at first. It may have completed a full turn in less than 10 hours. Its exterior glowed from residual heat, its interior churned with molten rock, and its early rotation was wild, unrestrained, and constantly modified by Earth's enormous gravitational pull. Over time, that first burst of molten energy faded, yet gravity kept working long after the surface cooled. The constant pull between Earth and the moon didn't just raise tides on our oceans, it raised tides inside the moon itself. Each stretch and release twisted its interior, creating friction that acted like an invisible brake. As Dr. James Williams of NASA's Jet Propulsion Laboratory explains, the moon's rotation slowed because tidal friction never stops. Energy isn't destroyed, it simply shifts from spin into heat and orbital motion. That frictional drag forced the moon to trade rotational speed for long term stability. The faster it once turned, the more dramatically Earth's gravity distorted it. With every rapid rotation, the moon's interior flexed its rocks, grinding and sliding against one another. It generated heat the same way Jupiter's moon Io does today, but on a scale the cooling moon couldn't maintain. According to estimates from the Lunar and Planetary Science Institute, early tidal forces inside the moon could have released up to 1019 joules of energy. That's enough to power all of human civilization for millions of years. None of that energy disappeared. It was absorbed into the moon's interior, altering its structure, reshaping its crust, and hardening the body we see today. As the moon's mantle cooled, it became increasingly rigid. Tidal flexing diminished, the internal heating faded, and slowly, very slowly, the moon's rotation dropped toward equilibrium. Within roughly the first 100 million years after its formation, its spin had slowed so much that it nearly matched its orbital period. One hemisphere began facing Earth more and more consistently. The far hemisphere gradually turned away forever. This transition was not smooth. Data from ESA's Smart 1 mission revealed stark differences between the near side and the far side. The near side, our familiar face, has thinner crust, smoother plains, and large dark maria, where ancient lava once seeped across the surface. The far side is thicker, rougher, and heavily cratered. This uneven split is not coincidence. It is the imprint of ancient gravitational stress. The near side, more directly pulled by Earth, remained warmer for longer and more prone to volcanic resurfacing. The far side cooled faster and hardened earlier. Dr. Maria Zuber of the Grail mission put it simply: the moon's shape is a memory of its motion, and we can measure that memory with extraordinary precision. Thanks to the retroreflectors left on the moon by Apollo 11, 14, and 15, scientists track the moon's orientation and distance down to millimeters. These measurements show that the moon's alignment has been stable for billions of years. Only tiny librations remain, subtle wobbles of just a few arcseconds. These small oscillations are echoes of a time when the moon spun freely. If we could travel backward into that distant era, the sky above the young moon would be unrecognizable. Its surface was still molten, glowing from the heat of its birth. Earth would not hang motionless in the sky as it does today. Instead, it would sweep rapidly overhead, rising and setting every few hours, its surface shrouded in vaporized rock from the giant impact. The tides raised on both bodies would have been unimaginable waves of molten material rising and collapsing, crust cracking oceans of magma, shifting beneath a sky dominated by a glowing, swollen earth. Those forces, violent and persistent, are what eventually forced the moon to surrender its freedom and settle into the silent, synchronized rotation we see now. NASA's high-resolution simulations, released in 2023, reveal that the moon's early rotation and its widening orbit were never separate events, they evolved together. As the moon gradually lost spin, it drifted farther from Earth, just as it continues to do today. That slow recession, now measured at 3.8 centimeters per year, is the faint modern echo of an ancient breaking process. Every tiny outward step represents rotation, surrendered energy, traded for distance. And this behavior isn't unique. Across the solar system, astronomers see the same gravitational choreography repeating itself. Pluto and Charon, for example, are so deeply intertwined that both bodies keep the same face toward each other, a mutual tidal lock. Mercury, influenced by the Sun's immense gravity, fell into a 3-2 spin orbit resonance, completing 3 rotations for every 2 orbits. These cases show that wherever gravity acts long enough, tidal forces sculpt motion into predictable patterns. For our moonful, synchronization is believed to have settled around 3 to 3.5 billion years ago. From that point onward, the lunar day and lunar orbit aligned almost exactly. The restless young world hardened into the calm companion we recognize today. It seems unmoving, but that stillness is the surface expression of a deeper balance between inertia driving motion forward and gravity pulling it toward order. Inside the moon, the memory of this transformation is still present. Data from the Grail mission reveals stress lines, density pockets, and crustal asymmetries, geological scars produced by billions of years of gravitational flexing. These interior signatures confirm that the moon once rotated far faster than it does now. If we could watch this history unfold in fast motion, It would resemble a spinning top, slowly losing speed. It wobbles, steadies, and eventually falls into a state where its motion matches the rhythm of its environment. That's exactly what the moon experienced, not over seconds, but over millions of years. Rotational, kinetic energy drained away, while orbital angular momentum increased. The Earth Moon system's total momentum stayed constant exactly as Newton's laws require, but its distribution changed. Spin became orbit, motion reorganized into stability. As Neil deGrasse Tyson once noted, in space, everything tends toward balance, and balance is never truly still. The moon's apparent stillness is the end product of a long mechanical evolution, not an absence of motion. When the last remnants of internal heat dissipated and the mantle grew rigid, the moon's orientation toward Earth became locked in place. Any slight deviation would create a restoring torque, snapping it back toward alignment. It settled into a natural energy minimum, a configuration so stable it has survived billions of years of meteor strikes, seismic tremors, and subtle orbital shifts. If we could peer back into its early era, when its crust glowed, its rotation was swift, and molten plains heaved beneath a haze of vaporized rock, we would see a very different moon. A world alive with motion, losing energy, reshaping itself under Earth's relentless pull. But the moon that remains today is the preserved outcome of all that change, a sphere that no longer spins freely, yet carries the imprint of every rotation it once had. Its surface, its orbit, and even its effect on Earth's tides are relics of that long evolution. So when you look up at the familiar face in the sky, remember it wasn't always the same. What you see now is the quiet survivor of an ancient fading spin held in perfect restraint by gravity's patient hand. Part 4. What does the hidden side of the moon really look like? For most of human history, the moon seemed like a familiar companion, steady, unchanged, and always showing the same luminous face. Yet for thousands of years, half of it remained completely invisible, a hemisphere sealed away not by mystery, but by orbital mechanics. Then, in 1959, that silence finally broke. A small Soviet probe named Luna 3 slipped behind the moon and pointed its camera toward the unseen. In that moment, humanity witnessed something no one on Earth had ever observed: the moon's far side, stark and profoundly different from the world we thought we knew. Luna 3 transmitted just 29 grainy images across nearly 400,000 kilometers, but the impact of those photos was immediate. Instead of the broad dark Maria that defined the near side, the far side appeared chaotic, crowded with craters, jagged highlands, and ancient scars. The two hemispheres looked less like twins and more like two separate worlds fused into one. Subsequent missions revealed just how real that divide is. NASA's Lunar Reconnaissance Orbiter, LRO, provided detailed topographic maps showing that the far side's crust is on average about 15 kilometers, 9 miles thicker. That added thickness acted like a natural barrier. Billions of years ago, when meteor impacts fractured the surface and molten rock surged upward, the near side's thinner crust allowed lava to flood basin after basin, forming the dark seas visible from Earth. The far side's thicker shell prevented the same flows leaving its surface, frozen in its early heavily cratered state. Chemical data from missions like Clementine and Smart 1 deepened the mystery. The near side contains higher concentrations of iron and titanium materials that lower the melting point of rock making volcanic eruptions more likely. The far side, with its abundance of aluminum and calcium, reflects a colder, more rigid geological past. Many scientists, including Dr. Noah Petro of NASA's Goddard Space Flight Center, believe Earth itself helped create this imbalance. In the Moon's youth, Earth's gravitational influence may have drawn heat producing elements toward the hemisphere facing us, leaving the far side cooler, thicker, and less active. Because of this asymmetry, the far side became a kind of cosmic archive during the late heavy bombardment between 4.1 and 3.8 billion years ago. Both hemispheres endured catastrophic impacts. But while lava resurfaced much of the near side, the far side kept almost every crater a geological memory carved into stone. The most dramatic of these is the South Pole Aitken Basin, an enormous impact structure stretching roughly 2,500 kilometers, 550 miles across, and plunging as deep as 8 kilometers, 5 miles. It is one of the largest and oldest impact sites in the entire solar system. Grail's gravity measurements reveal that the collision was so powerful it may have excavated material from the moon's mantle itself, creating one of the only natural windows into its deeper composition. Seen this way, the hidden hemisphere is not merely the moon's dark side, but its ancient side of the landscape, left almost untouched since the solar system's earliest chapter. Where the near side smoothed itself over with fire, the far side preserved its wounds in silence. And every ridge, every crater, every jagged shadow tells the story of a world shaped unevenly by gravity, heat, and time. When NASA's Lunar Reconnaissance Orbiter began its global survey in 2009, it delivers something humanity had never possessed: a detailed, high resolution map of the moon's hidden hemisphere. Using its narrow angle camera, capable of resolving features smaller than a single meter LRO, revealed a terrain that feels almost turbulent, as if the surface had been caught in a storm that froze mid-motion. Craters stack upon craters. Ejecta rays radiate across hundreds of kilometers. Ridges, pits, and fractured valleys weave together into a portrait shaped by billions of impacts, with almost nothing to erase them. A few regions, such as the dramatic Tsiolkovsky crater, display volcanic traces, dark flows, and smooth floors, hinting that molten rock once pushed its way to the surface. But these pockets of activity are rare. The far side's crust is too thick, too rigid, too cold to have sustained widespread volcanism like the near side. LRO's Diviner Radiometer added another dimension to this starkness temperature. During the 2-week lunar night, far side temperatures plunge below 230 degrees, 382 GF, reaching lows colder than any natural environment on Earth. Without Earthlight reflected sunlight from our planet, the far side endures deeper, longer freezes, creating an even more hostile landscape. Mark Robinson, LRO's principal camera investigator, summarized the view with clarity that borders on poetry. The far side is a geological museum. It's a place where nothing has reset the surface for billions of years, where each crater preserves the memory of the solar system's violent youth. In many ways, it is the closest thing we have to a time capsule from the era when planets were still forming. Modern exploration has added new layers to this story. In 2019, China's Chang'e 4 spacecraft achieved the first soft landing on the far side, touching down in the von Karman crater inside the immense South Pole Aitken Basin. Its rover U-22 continues to analyze the area's minerals and subsurface structure. The data it sends home via a relay satellite stationed at the Earth Moon L2 point suggests that materials on the surface contain olivine and low calcium pyroxene minerals that may originate from the moon's mantle. Findings that NASA scientists had predicted decades earlier are now being confirmed directly from the ground. Yet what stands out most is not what the far side reveals, but what it refuses to show. There are no vast basalt seas like Mare Imbrium, no smooth plains like Mare Tranquillitatis, no dark patches that soften the appearance of the near side. This hemisphere is raw, rugged, and fundamentally different. It is a second moon attached to the first. This stark contrast creates opportunities and challenges. Because the far side never faces Earth, it sits in one of the quietest radio environments in the inner solar system. Shielded from our planet's constant electromagnetic noise, it is ideal for low frequency radio astronomy. NASA and ESA have proposed missions to place radio antennas on or beneath its surface, hoping to catch signals from the universe's dark ages, the time before the first stars ignited. These whispers from the early cosmos are drowned out on Earth, but on the far side the silence is profound. Reaching that silence, however, isn't simple. Spacecraft on the far side cannot communicate directly with Earth, so every mission requires a dedicated relay satellite, like China's Kuiqiao, which has maintained a stable link from the Earth Moon L2 point since 2018. This infrastructure marks a turning point. Humanity now possesses a continuous communication bridge to a place once entirely beyond reach. And if you could stand on that remote hemisphere tonight, the experience would feel surreal. The familiar earth bright, dominating always present in the sky of the near side would be absent. The horizon would arch beneath a sky filled only with stars. If you were standing on the far side of the moon, the sky would feel almost unreal. Earth would never rise, never set, never appear. Instead, the stars would burn with a clarity impossible from any point on our planet. No atmosphere, no reflected glow, no interference. The Milky Way would cut across the darkness like a river of frozen light, and around you every footstep would echo across a landscape untouched for billions of years. This desolate beauty is not random. It is the direct consequence of tidal locking. Because the far side never turns toward Earth, it has endured billions of years without the slight protective effect of Earth's gravitational sweep. The near side, our familiar moon, sits inside a partial gravitational shield. Earth intercepts a portion of the meteoroids and debris that enter the Earth Moon system. But the far side faces the universe alone. It absorbs nearly everything that space throws at it. It's a harsh symmetry. The side we see is smoother, darker, in patches comparatively gentle. The hidden side is ancient, battered, and brutally exposed. Both faces belong to the same world, but each records a different era of lunar history. As Neil deGrasse Tyson once noted, the far side is not dark, it's merely unseen. And yet, what we cannot see has shaped the moon's evolution as profoundly as what we can. The first blurry images from Luna 3 and later the razor sharp mapping from LRO didn't simply show a new hemisphere. They transformed our understanding of how worlds age under gravity's long influence, how cooling crust thickness, orbital mechanics, and tidal stress sculpt a planetary body over billions of years. And that gravitational relationship is still unfolding right now. So, Part 5. Could Earth's gravity be slowly killing the moon's spin? Every moment the moon drifts a little farther away, about 3.8 centimeters per year. It's slow enough to feel irrelevant, yet over millions of years, it marks a continual, measurable change in the Earth-Moon system. The tidal forces that once slowed the moon into perfect synchronous rotation have not switched off. They are still active today, quietly adjusting the mechanics of the system. This outward drift is not speculation, it is directly measured. During the Apollo missions, astronauts placed arrays of retroreflectors on the lunar surface. By firing laser pulses from Earth and timing their return, scientists can measure the Earth-Moon distance with a millimeter precision. Those readings show a consistent, steady increase in separation, tiny but relentless. The cause is tidal friction, the same long-acting force that locked the moon's rotation billions of years ago. Here's how it works. Earth's gravity raises slight tidal bulges in the moon's rigid crust. At the same time, the moon raises much larger tides in Earth's oceans. But because both bodies rotate, these bulges never point exactly toward one another, they're always offset by a small angle. That offset creates torque, a twisting force that transfers energy from one form of motion to another. In this ongoing exchange, Earth's rotation slows, losing energy. The moon gains orbital energy, moving farther away. The total angular momentum of the Earth-Moon system stays perfectly conserved. NASA's Jet Propulsion Laboratory describes it as a trade of motion, a rebalancing that never truly ends. Earth's day lengthens by about 2 milliseconds per century, while the moon's orbit expands at a rate we can still measure with lasers. Even though the moon is already tidally locked, that doesn't mean the process has completed. Gravity continues to tug, stretch, and dissipate energy within the moon's interior just far more gently than it did billions of years ago. The lock is stable, but it is not static. The system keeps adjusting itself with microscopic precision. Modern lunar laser ranging projects, such as the Apache Point Observatory Lunar Laser Ranging Operation in New Mexico, now measure the Earth-Moon distance with astonishing precision. The uncertainty has fallen to just a few millimeters, and every data set, every pulse of returning light confirms the same story: the moon is drifting outward, exactly as predicted by Newtonian gravity and Keplerian orbital dynamics. A slow, steady exchange of energy that has been unfolding since the moon first formed. To picture this, imagine Earth's oceans acting as enormous mobile brakes. The moon's gravity raises a pair of tidal bulges on opposite sides of Earth, but because Earth rotates faster than the moon completes an orbit, those bulges never point directly at the moon. They are carried slightly ahead by Earth's rotation. This tiny misalignment creates a forward tug on the moon. It gives the moon a little extra energy each day, and that tiny push moves it into a slightly wider orbit. At the same time, those same tides pull back on Earth's rotation, slowing it by minute amounts. NASA's Goddard Space Flight Center notes that this process lengthens Earth's day by roughly 1.7 milliseconds every century, an increase so small that no human would ever notice, yet so precise that atomic clocks record it without fail. Project that forward, and hundreds of millions of years from now, Earth's day will last pause more than 25 hours. What makes this even more remarkable is that the mechanism responsible for locking the moon's rotation billions of years ago is still operating, only now its effects are gentler, more subtle. The moon no longer loses rotational energy. It is already synchronized with its orbit. But the Earth-Moon system continues to redistribute energy, with Earth's rotation feeding the moon's outward drift. The lock is secure, yet the gravitational conversation continues. Astrophysicists often describe this as gravitational aging. As the moon moves farther away, its orbital speed gradually slows. It currently travels around Earth at about 1 km/s, but that value will continue to decline as the orbit expands. With increased distance comes weaker tidal coupling, and with weaker coupling, the outward drift slows. Eventually, in the far future, the process will approach a stable mutual lock. In that distant era, Earth and Moon will face each other permanently. Earth will rotate once in the same time the Moon completes one orbit. One hemisphere of Earth will always hold the Moon fixed in the sky. The opposite hemisphere will never see it again. It will be a binary system in perfect gravitational symmetry. Dr. Jack Lissauer of NASA's Ames Research Center explains it simply: Earth is moving toward the same destiny as the Moon. It's a slow dance toward mutual capture. Until that distant equilibrium arrives, tidal friction continues to sculpt our world in measurable ways. Every rising tide, every shifting shoreline, every surge of ocean water is part of a global redistribution of energy, tiny on their own, but enormous in aggregate. Estimates suggest that around 3.7 terawatts of power, roughly equal to humanity's total energy consumption, is dissipated as heat in Earth's oceans each year due to tidal friction. None of this energy disappears. It is transformed, spread across millions of square kilometers of moving water. That energy is steadily converted into orbital momentum, nudging the moon outward, centimeter by centimeter. This is the hidden engine beneath the tides. This is the quiet mechanism still altering the moon's orbit today. Modern lunar laser ranging experiments, like the system operated at the Apache Point Observatory in New Mexico, have refined our measurements of the Earth Moon distance to astonishing precision. With uncertainties down to just a few millimeters, these observations trace the moon's outward drift exactly as classical mechanics predicts. Every dataset matches Newton's gravitational laws and Kepler's orbital equations perfectly, a slow trade of motion stretching across billions of years. To picture what's happening, imagine Earth's oceans acting like massive fluid brakes. The moon's gravity pulls on the oceans and raises two tidal bulges, one facing the moon, one on the opposite side. But because Earth rotates much faster than the moon orbits, those bulges are carried slightly ahead of the moon. That tiny offset creates a forward tug on the moon, giving it a small boost in orbital energy and pushing it into a slightly wider path around Earth. Meanwhile, this same gravitational interaction drags on Earth's rotation, stealing a minute fraction of its spin every day. According to analyses from NASA's Goddard Space Flight Center, this tidal braking lengthens Earth's day by about 1.7 milliseconds per century. Over millions of years, those tiny additions accumulate. Far in the future, a terrestrial day will last more than 25 hours. What's remarkable is that the mechanism responsible for locking the moon billions of years ago is still operating. The moon no longer adjusts its spin, it's already synced with its orbit, but the Earth Moon gravitational partnership continues to exchange energy. The system hasn't stopped, it's simply shifted into a slower, or quieter phase. Astrophysicists describe this long term evolution as gravitational aging. As the moon drifts outward, its orbital speed drops. Today, it moves at about 1 kilometer per second, but that velocity will slowly decrease as the distance grows. And the farther the moon moves, the weaker the tidal coupling becomes. Eventually, billions of years from now, this exchange will naturally settle into equilibrium. In that future state, Earth will rotate once for every lunar orbit. The two worlds will be completely synchronized. One side of Earth will hold the moon fixed in its sky forever. The opposite side will never see it again. It will be a binary system locked in perfect symmetry. Dr. Jack Lissauer from NASA's Ames Research Center describes this evolution. Simply, Earth and Moon are slowly capturing one another. It's a long, steady dance. Until that final configuration arrives, the tides continue to sculpt both worlds. Every incoming wave, every outward pull of the ocean, every shifting shoreline contributes a microscopic amount of energy to the moon's expanding orbit. In total, roughly 3.7 terawatts of energy, nearly equal to the entire annual power consumption of human civilization, is dissipated as heat in Earth's oceans each year due to tidal friction. Spread across millions of square kilometers of moving water, that energy is gradually transformed into orbital momentum, nudging the moon outward one tiny step at a time. This is the quiet engine beneath the tides. This is the invisible mechanism that still shapes the Earth-Moon system today, precise, silent, and ongoing. Until that distant balance arrives, we're living through a temporary chapter, an in-between era, where the moon is still inching away. Earth is still spinning slightly too fast, and the gravitational handshake between them continues to evolve. Every night sky we look at is only a single frame in a much longer process. The tides washing onto our shores, the daily rise and fall of the oceans, are the visible traces of that ancient and energy exchange still unfolding. Earth's gravity isn't destroying the moon's motion, it's smoothing it out, shaping it, refining it. 1 centimeter at a time, the system is steering itself toward stability. And as the moon drifts outward, Earth's own rhythm shifts with it, a quiet reminder that nothing in the universe holds still, not even the bond between our planet and its oldest companion. Moon. Part 6. What if the moon suddenly began spinning again? Imagine just for a moment that the moon broke its silence. Imagine something, a massive impact, a gravitational disturbance, a deep interior shift forced it to rotate freely again. For billions of years, it has turned in perfect synchrony with its orbit, one hemisphere locked toward Earth. But what if that lock snapped? This isn't fantasy. Astrophysicists have run models for exactly this scenario, and the consequences would be dramatic, cascading through the Earth Moon system in ways both surprising and devastating. To understand why we start with the balance that exists now, the moon's synchronous rotation is the result of a delicate interplay between rotational energy, gravitational torque, and long term tidal friction. Break that equilibrium, and the first and most immediate effects would unfold here on Earth. Right now, the moon's gravity sculpts our tides, raising and lowering vast masses of water across Earth's surface. This cycle controls coastal environments, regulates ocean currents, and helps distribute heat around the planet. If the moon suddenly spun faster, even by a small fraction, its tidal bulges would wobble and drift unpredictably. High tides might arrive hours earlier or later. Low tides could weaken or intensify without warning. Some coastlines could flood more often, others might fall eerily calm. As NASA's Goddard Space Flight Center notes, tides are not just an ocean phenomenon, they influence the entire Earth system. Change the moon's rotation, and you restructure how energy flows across the planet. But the more profound consequences would unfold on the moon itself. After billions of years locked in place, the lunar interior has relaxed into a stable configuration. Its solid crust, semi molten mantle, and compact metallic core have long adapted to minimal internal motion. Introduce rotation again, even modest rotation, and that peaceful equilibrium shatters. Internal stresses would surge. The crust could fracture. The thick far side, colder and more rigid, might break violently under the strain. Models of lunar geodynamics show that a rotational increase of only about 10% could generate seismic waves strong enough to ripple through the entire lunar body. The moon already experiences moonquakes. Apollo seismometers recorded shallow quakes, reaching magnitude 5 triggered only by tidal flexing. If rotation returned, those quakes would intensify dramatically. The lunar surface, which has remained almost unchanged for eons, could begin to shift. Dust and regolith might cascade down crater walls. Long, stable landscapes would deform. The moon's appearance, the face humanity has memorized for thousands of years, would begin to alter. But the most far reaching effect lies not in tides or moonquakes, but in something deeper, the moon's role in stabilizing Earth itself. For millions of years, the moon's gravitational pull has kept Earth's axial tilt steady at around 23.5 degrees. That tilt is the quiet architect of our seasons, the reason climate zones remain stable, and the foundation of Earth's long term environmental rhythm. If the moon's rotational state changed even slightly, the gravitational grip that holds Earth's axis steady would weaken. Over long spans of time, the tilt could begin to drift unpredictably. Simulations from NASA's Ames Research Center show that without the moon acting as a stabilizing weight, Earth's axis could oscillate wildly, anywhere between about 10 degrees and 45 degrees. Such swings would reshape the planet. Polar ice sheets would grow and collapse in irregular cycles. Deserts could shift into grasslands, while once lush tropics might freeze under long periods of low sunlight. Even the length of a day would shift subtly as angular momentum leaked back and forth between Earth and Moon. The quiet harmony that has defined Earth for billions of years would start to fracture. Picture an Earth where tides arrive at unpredictable hours, where seasons lurch from one extreme to another, and where the night sky shows a moon that never looks the same twice. The familiar face we've seen for every generation of human history would vanish. Each evening, a new arrangement of craters and shadows would rise constantly, turning, constantly altering. Lunar eclipses would distort. The moon's brightness would vary. For astronomers, orbital calculations would become a moving target. For life on Earth, it would mean a world shaken out of its long held balance. But what could cause such a disruption? For the moon to resume spinning freely, an enormous external torque would be required, something powerful enough to break a gravitational bond that has held for 4.5 billion years. A massive asteroid impact, perhaps tens of kilometers wide, could theoretically deliver that jolt. NASA's Near Earth Object Program notes that impacts on this scale are incredibly rare, but not impossible. Worlds across the solar system bear scars from such collisions. Some researchers believe Mercury's odd rotational behavior may trace back to ancient impacts that altered its spin and orbital resonance. If an event of that magnitude struck the moon, the shock could redistribute its angular momentum. The immediate aftermath would be catastrophic: vast ejecta plumes, debris arcs spreading through space fragments, potentially reaching Earth's upper atmosphere. Even a small shift in rotation would matter. NASA's current lunar gravitational models show that a mere 1% change in the moon's rotational period could raise tidal forces on Earth by up to 15%, a large enough change to affect ocean circulation and disrupt climate systems for centuries. Planetary scientist Dr. Håkan Svedhem once compared the Earth Moon connection to a pendulum tuned over billions of years. Disturb it suddenly, and the system loses its rhythm. And that's only the beginning. The moon's lock also stabilizes the shape and behavior of its orbit. If it started spinning, its internal mass distribution, known as the quadrupole moment, would gradually shift. That change would ripple outward, altering the eccentricity of its orbit over long timescales. The moon might begin traveling a more elongated path around Earth. The distance between the two worlds would vary more sharply. Tides would rise and fall with enhanced extremes. Nighttime light levels would change in repeating but erratic cycles. It wouldn't destroy Earth, but it would dismantle the gentle stability our world depends on. In the end, the deepest consequence wouldn't be the quakes or the tides or the shifting light. It would be the loss of the equilibrium that has governed Earth since life began. The moon's stillness isn't a curiosity, it's a structural element of the Earth Moon system. It keeps the tilt steady, keeps the rhythms repeatable, and keeps the exchange of energy between ocean, atmosphere, and planet in a narrow, life friendly range. Without this locked balance, the natural cycles that support ecosystems, weather, and climate would loosen and drift. Predictability would fade. Chaos would gradually take its place. Libration in longitude is the most noticeable of these hidden movements. Because the moon's orbit is not a perfect circle, but a slightly stretched ellipse, its orbital speed changes as it swings around Earth. When it moves faster near perigee and slower near apogee, its rotation can't adjust instantly to match. The result is a gentle horizontal sway that lets us peek a little farther around its eastern or western edges, revealing a sliver of terrain that normally lies just out of sight. It's a reminder that even in a gravitational lock, the moon's orbit still carries the memory of its ancient freedom. Libration in latitude comes from another subtle asymmetry. The moon's axis is tilted about 6.7 degrees relative to its orbital plane, and that tilt causes the moon to nod slowly over the course of a month. At some times, we see slightly more of the northern highlands. At others, a glimpse of the rugged southern terrain. This nodding motion is small, but across billions of years, it has allowed astronomers to map regions of the lunar surface that were never fully visible at first glance. Then there is diurnal libration, the tiniest of all, just a product of perspective. As Earth rotates each day, observers in different locations view the moon from slightly different angles. Someone watching from sunrise sees a little more of one edge, while someone at sunset sees a little more of the opposite. This shift is only about 1 degree, but it gently extends the portion of the lunar sphere we can observe, adding to the quiet complexity of the moon's apparent stillness. Together, these three librations create a slow, continuous rocking, almost imperceptible without precise instruments. NASA's Lunar Reconnaissance Orbiter has measured these motions with extraordinary accuracy, showing that the moon's orientation changes by mere fractions of a degree, yet enough to reveal thousands of square kilometers, more than a true half sphere. Even within its synchrony, the moon is never motionless. Seismometers placed during the Apollo missions detected tiny tremors, shallow moonquakes induced not only by tidal forces, but by thermal expansion as lunar day gives way to lunar night. Its crust creaks, contracts, and shifts in small bursts of energy. The moon continues to breathe heat from within, releasing the last remnants of ancient formation energy and tidal stress. Its orbit, too, is gradually evolving. With every passing year, as the moon drifts a few centimeters farther from Earth, its orbital period lengthens ever so slightly. Subtle perturbations from the sun from Earth's equatorial bulge and from the intricate gravitational interplay among inner planets all contribute to small variations in its path variations detectable today thanks to laser ranging experiments and high precision orbital modeling. So, when we say the moon is still, we are speaking only in human terms. In reality, it is in constant delicate motion, rocking, adjusting, responding. It follows gravitational rules written long before life arose, on Earth rules that continue to guide its dance with flawless precision. The face we see may never change, but its posture does shifting by degrees so fine that only instruments' equations and time itself can reveal the movement. In that sense, the moon is like a pendulum so perfectly balanced that we confuse its rhythm for silence. But the silence is an illusion. It is always moving, always adapting, always carrying the imprint of forces that shaped both it and our world. These subtle shifts reveal more than orbital mechanics. They uncover the moon's internal past layer by layer. Every tiny oscillation, every fraction of a degree of sway carries information about how the lunar crust cooled, how its mantle solidified, and how ancient impacts redistributed its mass. What we see through libration is not just movement, it is memory. High precision measurements from NASA's Grail mission show that beneath the moon's surface lie vast regions of uneven density remnants of colossal impacts that once shook the young moon to its core. These mass concentrations, mascons, act like hidden anchors, tugging at the moon's rotation with imperceptible force. Over millions of years, they subtly warp the lunar gravitational field, altering the fine details of its wobble. In the data, scientists can trace how individual basins like Imbrium and Serenitatis left fingerprints deep within the crust fingerprints that still influence the moon's motion today. Even the moon's cooling plays a role. As its interior gradually contracts, the distribution of mass shifts ever so slightly. The crust thickens in places, fractures in others, and these minute changes accumulate over geological time. The result is a slow evolution of its libration, tiny adjustments that instruments like LRO's altimeter can detect, but the human eye cannot. To us, the moon looks timeless. To physics, it is constantly refining its balance. This constant motion extends beyond rotation. The moon's orbit itself is never exactly the same 2 months in a row. Solar gravitational pull adds a gentle tug that stretches and compresses the orbit, a rhythm layered on top of the Earth Moon interaction. As sunlight warms the lunar surface, each day rocks expand. As night falls, they contract. These thermal stresses, measured by Apollo seismometers as thermal moonquakes, introduce small pulses of energy that reverberate through the crust. Even these vibrations, faint as they are, play a role in the moon's long term dynamical behavior. And then there is the influence of Earth's own imperfection. Our planet is not a perfect sphere. Its equatorial bulge exerts an uneven gravitational pull, nudging the moon's orbit just a little with each cycle. These nudges accumulate like whispers over epochs, shifting the orientation of the lunar orbit by degrees too small for early astronomers to imagine. Today, with high precision tracking, We can see these adjustments as clearly as clockwork. Together, these effects make the moon not a fixed lantern in the sky, but a world in continuous, elegant motion, a world that rocks and breathes in patterns shaped by physics older than life itself. When you look up and see a familiar face, you're witnessing only the average of countless small oscillations movements that keep the moon aligned, balanced, and subtly alive. In its stillness lies complexity, in its silence lies history, and in its gentle rocking lies the proof that nothing in the universe, not even the face of our oldest companion, is ever truly still. If we could watch the moon on a cosmic timescale, its motion would reveal itself like a slow heartbeat, each tilt, each shift, a breath drawn in gravity. What looks still to us is in reality a continuous pulse, a world adjusting itself moment by moment as forces flow through it. These tiny oscillations are more than elegant motions. They are diagnostic tools. They allow scientists to peer beneath the lunar surface into layers no probe has ever touched. By analyzing these microscopic variations, how the moon leans a little more one month or nods a little less, the next researchers can piece together the structure of its core. The most precise models, anchored by data from NASA's Lunar Prospector and the Grail mission, show that deep inside the moon still holds a partially molten heart. Its metallic outer core, liquid and responsive, interacts with the overlying solid mantle, subtly altering the moon's physical libration. Those tiny wobbles are fingerprints of heat density and motion far below the surface. This is why scientists treat lunar libration like a natural seismic instrument. The moon itself becomes the detector its movements recording processes hidden underground. Each fraction of a degree reveals something: how stiff the mantle is, how its crust thickened over time, how the inner layers have cooled and contracted. In a place where no seismic network exists except the ancient Apollo seismometers that still whisper data, these motions are priceless clues. The accuracy with which we track these motions today borders on unreal. With very long baseline interferometry, radio telescopes scattered across Earth can pinpoint the moon's position to within centimeters. Every slight change in trajectory, every minuscule shift in orientation is logged with mathematical precision. Over decades, these records have confirmed what theory predicted: that the moon doesn't simply orbit, it sways through space, nudged gently by Earth, by the sun, and by its own uneven mass. Even sunlight plays a role. As lunar daylight warms rocks and nighttime cools them, the surface expands and contracts with a faint crackle. These thermal stresses add tiny shivers to the moon's crust, subtle enough to escape the naked eye, clear enough for sensitive instruments to detect. The sun's gravity contributes too, adding periodic variations that combine with Earth's pull to shape the moon's slow, elegant wobble. Dr. Noah Petro captured it with perfect clarity. The moon is always moving. We simply live too slowly to notice. And he's right. Our human perception collapses these long, sweeping motions into a static picture. We see a lantern in the sky, unchanging, serene. But in truth, the moon is never still. It rotates in synchrony, rocks, in longitude and latitude, precesses in its orbit, drifts outward each year, and flexes under the constant tug of Earth's gravity. If time flowed faster, for us even just a little, we would see a different moon entirely. Its face would sway like a pendulum. Its orbit would widen like a slowly unfurling spiral. Its poles would dip and rise. Shadows would crawl across craters in a complex dance. The stillness would dissolve into motion, and the motion into rhythm. All of this motion, delicate as it seems, serves a purpose. It keeps the Earth Moon system flexible and stable at once. These tiny oscillations allow the gravitational lock to adjust rather than fracture, to tighten rather than break. They are the silent regulators that have kept both worlds in balance for billions of years. And so, when we lift our eyes toward that quiet silver disk, the stillness we see is not the absence of movement. It's the result of perfect motion, so slow, so steady, so ancient, that our lives are too brief to witness it. Others, like Pluto and Charon, achieved a rare state of mutual locking, where each world keeps the same face toward the other, turning in a kind of quiet, gravitational embrace. But Earth and its moon, their synchrony is cleaner, tighter, and more stable than almost any other pair we know. To understand why we have to go back to the beginning, not just of the moon, but of the Earth itself. The giant impact hypothesis gives us the first clue. When Theia struck the young Earth, the debris that became the moon formed unusually close and unusually large. That meant the newborn moon felt Earth's gravity more strongly than most satellites ever could. Stronger gravitational pull meant stronger tidal forces. Stronger tides meant faster energy loss. And faster energy loss meant a quicker path to synchronization. In other words, the lock wasn't a miracle. It was the natural consequence of a violent beginning. As the young moon orbited Earth in those early ages, its rotation raised a head spinning independently like a glowing ember. But those tidal bulges raised by Earth acted like anchors. Each time the moon rotated slightly too fast, gravity pulled against the bulge, slowing the spin. Each time it rotated slightly too slow, the torque corrected it in the opposite direction. Billions of tiny adjustments, microscopic braking events, gradually carved the moon into perfect rhythm. Scientists describe this process with an elegant rule. A tidal lock is the lowest energy state available to a two-body system. Once the moon reached that state, the system clicked into place. And from that moment, the lock became self-reinforcing. Any attempt to drift out of alignment produces a restoring torque gravity's way of saying return to equilibrium. But here's where the story becomes even more extraordinary. Most tidally locked moons orbit gas giants, whose immense mass forces synchronization quickly. Earth, by contrast, is small compared to Jupiter or Saturn. For our planet to lock a moon this large, the circumstances had to be exceptionally precise. The right impact, the right amount of debris, the right initial distance, the right early rotation rates, the right dissipation of heat inside the moon, and the right orbital evolution over billions of years. Had any of these factors differed even slightly, the lock might never have formed or might not have been stable for long. NASA's GAS models suggest that if the moon had been only 10 to 15% smaller, or if Earth had rotated just a little faster in its first 100 million years, the lock could have taken billions of years longer to form, or it might have settled into an unstable resonance, like Mercury's 3-2 cycle. Instead, the Earth Moon system fell into what astrophysicists call a dissipative attractor, a state toward which the system naturally evolves and from which it rarely escapes. The universe wasn't aiming for perfection, yet the outcome looks remarkably precise. This raises the deeper question scientists still debate. Was this synchrony inevitable once the moon formed, or was it a rare accident of initial conditions? From a physics standpoint, the answer leans toward inevitability. Any large satellite orbiting close to a solid planet would gradually lose its rotational freedom. Gravity demands it. But from a planetary formation perspective, what happened between Earth and the Moon is anything but ordinary. The size of the impact, the mass of the Moon, the distance at which it formed, and the cooling behavior of both bodies produced a synchrony far cleaner than typical. It's the combination that makes it extraordinary common mechanism, uncommon outcome. So the harmony we see today isn't magic, nor is it coincidence. It is the quiet result of billions of years of energy draining away motion, slowing mass shifting, and gravity sculpting both worlds into the most stable arrangement they could achieve. A balance so perfect it feels deliberate, even though it is purely the work of natural laws acting with unimaginable patience. In this sense, the Earth Moon system behaves more like two partners locked in a long, steady exchange than a dominant planet controlling a small satellite. Their motions influence each other, their histories intertwine, and their equilibrium emerges from the shared evolution of both bodies, not from one alone. As the moon cooled, thickened, and settled into its present asymmetrical shape, Earth's rotation slowed and its tides grew gentler, two worlds converging toward a configuration that wastes the least energy. The remarkable part is how elegantly the pieces fit together. As orbital simulations from NASA and ESA show the moon's mass distribution, its offset center of gravity, its dense mascons, its thinner near side crust, makes the current tidal lock not just stable, but remarkably resistant to disruption. Even small perturbations from the sun planetary alignments or internal lunar shifts fail to break the synchronization. Each disturbance is absorbed, corrected, and balanced by the same gravitational feedback that has preserved this rhythm for billions of years. This is why some planetary scientists argue that the lock was not merely a coincidence, but the natural endpoint of the system's evolution. Once the Earth Moon pair formed under the extreme conditions of the giant impact, the mathematics of celestial mechanics left it only one long term outcome: a synchronized rotation, a stable orbit, and a gravitational equilibrium that could endure nearly indefinitely. Yet, even so, the refinement of this synchrony feels improbably precise. The moon's distance, about 400 kilometers. Its orbital eccentricity small but meaningful. The rate of Earth's rotational slowdown. The tidal dissipation factors inside both worlds. All of them combined to shape the lock into the tightly tuned system we witness today. Shift any of those parameters slightly in the early solar system, and the outcome might have been different. A moon that wobbled chaotically, or drifted outward too fast, or fell into an unstable resonance instead of a perfect lock. But that isn't what happened. What we see now is the product of billions of years of gravitational negotiation rotation, traded for orbit, heat, traded for stability, asymmetry, transformed into harmony. The moon's face toward us became fixed not through chance alone, but through the gradual settling of a system seeking the most efficient distribution of energy possible. That's why the Earth Moon pair stands apart. It is governed by the same rules that guide every moon in the solar system, yet shaped by conditions so unusual that the result looks almost intentional, a synchrony that holds steady across deep time, anchoring Earth's tides, seasons, and axial stability. And as the system continues to evolve, the lock only tightens. Each centimeter, the moon drifts outward. Each millisecond, Earth's rotation slows, brings the pair closer to a final state, billions of years in the future, mutual tidal, locking two worlds forever, facing one another in a timeless gravitational embrace. To trace that perfect balance back to its origin, we have to return to a time when the solar system was young, a swirling arena of molten worlds, unfinished planets, and violent collisions. The Earth Moon harmony we see today is the final movement in a story that began in fire and chaos long before any stability existed. More than 4.5 billion years ago, the early Earth was still forming, gathering material from the protoplanetary disk. Its surface was a rolling ocean of magma, its atmosphere thick with vapor and dust. Into this young world came another body, a Mars sized protoplanet we now call Theia. Their paths crossed not by design, but by the statistical inevitability of billions of objects orbiting a newborn star. The collision was catastrophic, a glancing world shaping strike that tore molten rock from Earth's mantle and hurled it into orbit. Supercomputer simulations run by NASA's Ames Research Center show that within hours, that debris stretched into a glowing disk encircling the planet. Over months and years, it cooled, condensed, and gathered into what would become the moon. In this sense, Earth and Moon were born from the same wound, sharing its faint material, the same heat, and the same early momentum. It was here in the aftermath of the impact that the seeds of the tidal lock were planted. The newborn moon orbited much closer than it does today, perhaps only 20,000 to 30,000 kilometers above the molten Earth, enormous in the sky, its surface still radiating the heat of formation. At that distance, tidal forces were immense. Earth pulled fiercely on the moon's partially molten interior, raising colossal tides of rock flexing and heating it with every orbit. Those tides slowed the moon's rotation, dramatically draining energy from its spin and transferring it to its orbit. Bit by bit, rotation yielded to resonance. The moon's wild early spin eased. The tidal torque weakened. The crust cooled, thickened, and began to preserve the asymmetry that would help lock one hemisphere toward Earth forever. What looks like perfect design today was shaped by billions of years of grinding physics torque, friction, deformation, and cooling all unfolding in a choreography too slow for human senses, but exact enough to sculpt a stable world. Even Earth was transformed by that ancient handshake. Its axial tilt steadied, its days lengthened, its climate gradually found a rhythm that life could eventually inhabit. Tides smoothed the chaos of its early oceans, spreading heat, stirring minerals, and setting the stage for chemistry to bloom into biology. So, when we look at the Earth Moon pair now, we are seeing not an accident, but the result of deep time. A partnership forged in violence, settled into harmony, and held together by the same laws that shape every star, planet, and moon in the cosmos. And as we follow this history deeper, the question becomes unavoidable. What did the sky look like in those early days when the moon was young, the orbit was tight, and the tidal forces were far stronger than anything we see now? If this model is correct, the moon did not simply orbit the infant Earth. It emerged from the same incandescent cloud of vaporized rock, crystallizing as the system gradually cooled and separated into two distinct bodies. In that early era, there was no clear boundary between planet and satellite, only a turbulent glowing mass slowly organizing itself under the rule of gravity and heat. As the moon solidified and drifted outward, the violence of its formation remained etched into its surface. The far side's thick crust, the near side's basaltic plains, the frozen scars of impacts, all of them are direct consequences of how the young moon cooled unevenly inside the distorted gravitational environment left by the impact. Grail mission data later revealed something extraordinary. Deep within the moon, beneath its ancient crust, lie fossil remnants of tidal deformation, frozen patterns of stress that match precisely what we'd expect if the moon once endured extreme gravitational stretching while still molten. These buried scars are physical evidence of its chaotic birth. Even the little details tell the story. The distribution of Mascon's pockets of dense material beneath the lunar surface aligns with ancient impact basins filled by lava long after the Theia collision. Their shapes, densities, and gravitational signatures all confirm a world that was once fluid, reshaped repeatedly by tides and heat before settling into stillness. And yet, despite all that evidence of violence, the moon today appears impossibly calm. From Earth, it looks like a flawless sphere, suspended in silence, its face unchanged across human history. But that tranquility is deceptive. It is not the absence of motion or memory, it is the final stage of a world that burned, shattered, reformed, cooled, and finally froze into equilibrium. The stillness we see is simply the last frame of a story that began with unimaginable force. Every rock and crater is a leftover page, every ridge a signature of ancient tides, every dust grain a remnant of molten stone once thrown hundreds of miles into space. In that sense, the moon is not peaceful at all. It is the quiet service of a world that endured a cosmic catastrophe and survived. Its stillness is not serenity, it's aftermath. And the deeper we look into that aftermath, the more we uncover signs of that early chaos hidden beneath the calm face we know. For in the moon's frozen rotation, its layered crust, its gravitational asymmetries, and its drifting orbit lies a single unbroken thread connecting the violent past to the perfect synchrony we see today. Seen from that perspective, the moon's calm presence becomes even more extraordinary. A system that began in fire, molten rock hurled into orbit, seething tides inside a half formed world, has cooled and settled into one of the most stable gravitational relationships known. What started as chaos gradually crystallized into order, a long descent from violence into balance. NASA's Lunar Science and Exploration Program calls this a dynamic equilibrium, a state where opposing forces don't cancel out, but instead flow around one another until they find harmony. It's the same universal pattern that shapes everything from the formation of stars to the rotation curves of galaxies, even down to the structure of atoms. Energy becomes motion, motion becomes organization, organization becomes stability. The moon's synchronous rotation, that perfect alignment of one orbit to one spin, is the quiet endpoint of that evolution. As tidal friction drained away its early rotational speed, the moon fell into the lowest energy configuration available. At that moment, rotation and orbit snapped into rhythm, locking the moon's face toward Earth forever. The great turbulence of its birth finally gave way to a stillness that looks almost eternal. Yet, even in that stillness, the memory of violence remains. Deep beneath the crust, the Apollo passive seismic network recorded signals that hint at fractures extending far into the lunar interior, scars likely created when the moon was still soft, deforming under massive tidal stresses. Later, the Grail mission revealed variations in density and gravitational structure that trace the paths of those ancient strains. The moon's frozen gravity field, as scientists call it, still holds the imprint of every force that twisted, stretched, or reheated it across billions of years. As Dr. Maria Zuber explained, the moon's gravity field remembers, and it remembers in exquisite detail. Even the moon's most famous feature, the difference between the near side and the far side, is a fossil of its fiery beginning. The near side's thinner crust and dark mare plains likely formed because that hemisphere faced Earth's incandescent post-impact heat for thousands of years. That warmth slowed its cooling, allowing magma to remain mobile longer and eventually flood the great basins we see today. Meanwhile, the far side, insulated from Earth's radiant heat, cooled more quickly. Its crust thickened, hardened, and preserved nearly every impact from the early solar system. That asymmetry, painted across an entire world, has lasted for more than 4 billion years. It is the moon's oldest memory, the first imprint of its existence. And as the moon continues to orbit us in perfect quiet, that ancient record remains locked in stone, telling the story of a world born in fire, yet destined for balance. This relationship between destruction and balance isn't rare at all. It's the architecture of the universe. Everywhere we look, the same script plays out in different scales: collapsing gas clouds, settling into star systems, turbulent nebulae, giving birth to orderly fusion cores, colliding galaxies, smoothing into spirals and ellipses over millions of years. The Earth-Moon system is simply our local example of this cosmic pattern disorder reshaping itself through gravity, cooling, and time. If we could slow the Theia impact to a fraction of its speed, the sequence would feel strangely familiar. First chaos, then compression expansion, and finally equilibrium. The same pattern governs a star igniting hydrogen, a planet capturing an atmosphere, even a molecule finding its lowest energy bond. Energy flows until it finds stability, until motion settles into rhythm. When that happens, stillness isn't the absence of activity, it's the visible sign that balance has finally been reached. In that sense, the moon's silence does not conceal its violent beginning. It is that beginning transformed. The quiet face we see each night is the cooled afterimage of a world once torn apart, its molten fragments sculpted by gravity into something steady enough to guide our tides. The proof of its birth hasn't disappeared. It's written into every centimeter of drift, every gentle wobble, every tidal pulse on Earth that still responds to the moon's tug. As Dr. Neil deGrasse Tyson once noted, the moon is a witness not of peace, but of the moment Earth learned how to keep time. Through its motion and its stillness, we can trace the story of balance taking shape. That first impact didn't just create a moon, it helped create a world capable of life. Our stable tilt, our predictable seasons, even the cycles that govern climate and biology, are byproducts of the Earth Moon partnership born from that single catastrophic collision. Without Theia, Earth would be a different world entirely, perhaps lifeless, perhaps unstable, perhaps unrecognizable. So the soft glow in the night sky is not merely tranquil, it is the fossil light of a calamity long cooled, of violent beginning, refined into the most delicate equilibrium. Part 10. Will the moon ever escape or stop facing Earth one day? A single Earth day will last as long as an entire lunar month. The oceans will no longer surge and retreat, and far above the moon will hang unmoving in the sky, fixed forever over one hemisphere. This isn't imagination. It's the endpoint of a process already underway. Right now, the moon is drifting away from Earth at roughly 3.8 centimeters per year. We know this with extraordinary precision thanks to NASA's lunar laser ranging experiments, which have bounced light off the Apollo retroreflectors for more than half a century. That outward drift is powered by tidal friction, the same force that once slowed the moon's rotation and locked one hemisphere toward us. But that tidal exchange didn't stop when the lock formed. It's still happening quietly through every shifting tide on Earth. To understand where this leads, we follow the rules of orbital mechanics. Each time Earth rotates, the tidal bulges raised by the moon do not align perfectly beneath it. Earth spins faster than the moon orbits, so the bulges are dragged slightly ahead. That offset tugs the moon forward, giving it a tiny push in its orbit. The push adds angular momentum to the moon and steals it from Earth's rotation, lengthening our days by fractions of milliseconds each century. And as long as Earth continues to spin faster than the moon moves around us, the moon will keep drifting away inch by inch, year by year, toward its final silent equilibrium. Meanwhile, Earth continues to give up a little of its own spin. The conservation of angular momentum allows no exceptions. Whatever the moon gains in orbital distance, Earth must surrender in rotation. Dr. James O'Donoghue, a planetary scientist who previously worked with NASA, describes it simply. It's a cosmic seesaw. Earth trades rotation, the moon takes distance, both move toward balance. That balance has a name: mutual tidal locking. It's the point at which Earth's rotation slows enough to match the moon's orbital period. When that day finally arrives, one side of Earth will forever face the moon, while the opposite hemisphere will live in permanent moonless skies. According to NASA's long-term orbital evolution models, this state lies tens of billions of years ahead, roughly 50 billion years in the future. Long before that, the sun will have swollen into a red giant and reshaped both worlds beyond their current forms. But as a closed gravitational system, the Earth Moon pair will keep drifting toward that final symmetry until outside forces interrupt. When that future equilibrium arrives, one Earth day will stretch to nearly 47 of today's days, mirroring the moon's slow month-long orbit. Tides will fade, ocean bulges will flatten, and the continuous exchange of energy between planet and satellite will come to an end because there will no longer be any offset between Earth's spin and the moon's motion. The system will settle into a temporary stillness, a matched rotation, two worlds turning together in a single frozen rhythm. But even that balance won't last forever. ESA's Solar and Planetary Dynamics Division explains that the Sun's own evolution will eventually reshape the system. As the Sun brightens and loses mass through stellar winds, Earth's orbit will slowly expand. Solar tides, almost negligible today, will grow more influential over eons, gradually tugging at Earth's rotation and nudging the moon's orbit outward in ways that overshadow lunar tides. When the sun enters its red giant phase, roughly 5 billion years from now, its swollen outer layers may engulf Mercury and Venus and destabilize the orbital paths of Earth and the Moon. If our world endures past that expansion, the Earth-Moon pair could drift into a wider, colder orbit around a dying star, slowly moving toward their final tidal lock as the sun collapses into a white dwarf. But survival is not guaranteed. Some orbital simulations suggest that as solar tides strengthen, they could subtly speed up Earth's rotation again, throwing off the delicate balance that drives the moon's outward drift and altering the path of the system entirely. NASA's Astrophysics Division expresses the future succinctly. The moon will never fall back to Earth. It will continue to drift outward until gravity friction and time reach their final quiet compromise. That final agreement between Earth and Moon isn't a fixed moment, but a slow, shifting endpoint. As the Moon drifts farther away, its orbital speed continues to fall from today's roughly 3,682 kilometers to progressively slower velocities. When the distance between the two worlds eventually doubles, the gravitational pull binding them will drop to just a quarter of what it is now. The tides we experience today, the steady twice daily rise and fall of the oceans, will shrink into faint undulations. With tidal friction disappearing, many of Earth's natural cycles will quiet. Ocean currents will weaken, heat will move less efficiently around the globe, and the gradual lengthening of Earth's day Now, about 1.7 milliseconds per century will finally stop. For the first time in 4.5 billion years, Earth and Moon will have no remaining kinetic debts to settle. The exchange will be over. The system will rest. But another question lingers in theoretical models. Could the Moon ever slip entirely free of Earth's gravity? Astronomers say it is technically possible, but only in the most extreme scenarios. To escape the Moon would need to surpass Earth's escape velocity, about 5,800 kilometers or 3,600 mph relative to our planet. Nothing in the Earth Moon system can naturally supply that much energy. Even the outward drift caused by tidal friction falls far short. The force decays too quickly with distance. So an escape is not the Moon's destiny. Instead, the far more realistic outcome is an eternal partnership, a slowing orbit, widening over eons, until the two bodies enter a final mutual lock. Earth's rotation will match the Moon's orbital period, and the pair will become a double world, turning in silent unison. From the Moon's surface in that future age, Earth will no longer arc across the sky. It will hang immobile, a fixed blue-white hemisphere, frozen above the horizon, never shifting, never setting, and from Earth, the change will be even more profound. One hemisphere of our planet will live under a permanent moon, a constant silver companion. The opposite hemisphere will be forever moonless. Human cultures built on lunar cycles, the waxing and waning, the glow of full moons, the geometry of crescents, would have no counterpart in that distant era. The sky would lose a rhythm older than humanity itself. Astrophysicist Neil deGrasse Tyson once described this future as the universe easing into equilibrium, not an ending, but a settling. And that is exactly what this far off stillness represents. It is not the absence of motion, but the natural conclusion of billions of years of energy exchanged between two worlds. Every system in the cosmos tends toward such balance eventually. Galaxies, stars, planets, even atoms. The Earth Moon pair is simply following the same universal script. And if one day, long after the sun has transformed and the solar system has changed beyond recognition, there are still observers standing on the remnants of Earth. They will look up and see a moon frozen eternally above the same horizon, the same craters, the same dark plains, the same expression carved in stone. Silent, unmoving, a companion bound by ancient motion finally at rest. It will be a kind of ultimate quiet, the final easing of tides, the final slowing of spin, the last soft settling of motion between Earth and Moon. And in that profound calm, something becomes clear. What appears motionless is simply movement that has reached its perfect end point. The Moon's stillness is not the absence of change. It is change completed. NASA scientists often say that nothing in the cosmos ever stops. It only reaches balance, and that is what awaits the Earth Moon pair. Will the Moon ever stop turning the same face toward us? Yes, but only when Earth's own rotation has slowed enough to mirror it. Only when both worlds fall into the same rhythm, turning together, presenting the same side to each other forever. On that distant future, Earth a single day will stretch to match a lunar month. The oceans will no longer breathe in steady tides. The sky will grow steady and unmoving, as though time itself has taken a long, peaceful breath. And when that moment finally arrives, perhaps the truest way to describe it is this: we think of the moon as the quiet one, but all along it is Earth that has been drifting gently toward sleep. If this journey through gravity and stillness has brought you even a moment of peace tonight, I'm truly grateful you've spent it here with me. A light touch on the like button or a gentle tap on subscribe does more than you might imagine. It helps me continue weaving these bedtime wanderings through science, space, and silence. And if you feel comfortable sharing, I'd love to know where you're listening from. Which part of this slowly turning world holds your night right now? Your words, whether just a few or many, feel like small lanterns scattered across the darkness, and I read each one with care. Until our paths cross again, beneath another quiet sky, rest deeply and dream softly of the world that still turns above us.